In this video, we are starting section 5.3 on structural induction. So this is a special type of induction that's helpful for proving results about things that are defined recursively. So with that in mind, our goals are to define functions recursively, and then to do the same for sets and other structures. And then we'll prove results about rooted trees and other structures using structural induction. So in this video, we will start this talk about recursive things by giving some recursive definitions of functions. Okay, so let's start by recalling the Fibonacci numbers, which are a sequence of numbers where the first two terms are 0 and 1, and then each subsequent term is the sum of the two previous terms. So the first two terms are 0 and 1, and then if I add them up, I'll get the next term, which is 1. And then if I add the two ones, I'll get the next term, which is 2, and then add the 1 and the 2 to get 3, which is the next term. And if I keep going, well, then I'll get 5, and then 8, 13, 21. I could keep going 34, and so on. I'll get the Fibonacci numbers in this way. So the two key components to how they are defined is, well, there's this basis step where I define some initial terms. So my first term, maybe I can label that as f0. That's 0, and then the next term, f1, is 1. Okay, and then there's this recursive step, which tells me how to create terms after that. And that recursive step is that fn is going to be equal to fn minus 1 plus fn minus 2, the two previous terms added together. And the recursive step starts showing up with this third term, which for me is when n is greater than or equal to 2, because my subscripts, I started it at 0 here and then 1 here, which means for this one, the subscript is 2. Okay, those are the two key parts to defining this sequence. So I could also express this instead as a function where the domain is non-negative integers and the output, the codomain is the integers with the two conditions written this way. Now my basis step would use function notation. So f of 0 is 0, and then f of 1 is 1, rather than this sequence notation. And then now I'm going to use function notation for the recursive step. So f of n equals f of n minus 1 plus f of n minus 2. And that applies for n greater than or equal to 2. Okay, so this gives us the idea for how we can define functions recursively in general. The two key steps are, in the basis step, we will specify values of the function for some initial terms. And then in the recursive step, we give a rule to find subsequent terms using previous terms. Okay, so let's take a look at another example. So in this next example, I have this function where the domain is non-negative integers and the codomain is integers. It's defined recursively by, I have this one initial value, f of 0 equals 5, and then I have this recursive rule, f of n equals 4 times f of n minus 1 minus 3, and that applies when n is greater than or equal to 1. So the problem says find f of 1, f of 2, f of 3. Okay, so here's my initial value, f of 0 equals 5, and then it says, well, as soon as I get bigger than that, when n is greater than or equal to 1, I'm going to start using this recursive rule, this recursive step. So if I do that for f of 1, I'm going to plug in 1 for the n, anywhere I have this. So I'll get 4 times f of 0 minus 3. So this is 4 times f of 0 is 5, and then minus 3. So I get 20 minus 3, which is 17. Cool. If I do the same thing with 2 and I plug 2 in for the n, I will get it equals 4 times f of 1 minus 3. So this is 4 times 17 minus 3. So that is 68 minus 3, and that is 65. If I do the same thing with f of 3, that equals 4 times f of 2 minus 3. So that's 4 times 65, and then minus 3. So let's see, this is 260 minus 3. 260 minus 3, and that is 257. And I have the values. I have the values of these first couple of terms in this recursively defined function. Okay, so, one of the reasons we care about recursively defined things is they show up really commonly in programming. It's very common to define functions and sets recursively. Think about things like lists in Python. Those are recursively defined. Okay, so let's flip the page here. Let's do another example. So, what if I have an explicit formula for a function, like f of n equals 3 to the n, where f is a function from the non-negative integers to the reals. And in this formula, the values that we're plugging in, there's a typo here. This should say not positive integers. This should say integers that are greater than or equal to 0. Okay, so I want to instead express this as a recursive formula. So to get a feel for that, let's plug in some values. So if I start off by plugging in 0, I will get 3 to the 0, which is 1. If I plug in 1, I'll get 3 to the 1, which is 3. If I plug in 2, I'll get 3 squared. And, I could just say what that is, like 9, but let's really break this down. This is 3 times 3. Okay. If I plug in 3, I'll get 3 cubed, which is 3 times 3 times 3. And if I keep going, 3 to the 4th is 3 times itself 4 times. So one of the things I might notice about this is, like in 3 to the 4th, it's 3 times, and then a 3 cubed shows up. So this is 3 times 3 cubed, and 3 cubed is the previous term. If I look at 3 cubed, it's 3 times, and then I have a 3 squared here. That's 3 times 3 squared. If I look at 3 squared, that's 3 times, and then I have just 3. So this is 3 times 3 to the 1, so it's 3 times the previous term. Does that work even before that? If I look at 3 to the 1, well, it turns out this is 3 times the previous term, 3 to the 0, because that's just 1. So this is 3 times 1. Okay, so in general, my rule is if I was looking at 3 to the n, this is going to be equal to 3 times 3 to the n minus 1. And just using an exponent property, I see that, yeah, that's 3 to the n. So, okay, now we have the idea. So my recursive definition can be, I'll let f of 0 be 1. The initial value is 1. But then after that, f of n will be equal to 3, it'll be equal to 3 times f of n minus 1, 3 times the previous value. And that's going to hold when n is greater than or equal to 1. And I got my recursive definition. Okay, recursively defined functions are what are called well-defined. And that means that the value of the function is determined unambiguously for any input. So what's an example of something that's not well-defined? So here's an example. Let A be B union C, and F be kind of defined in the following way. Let's say its domain is A, and this codomain, I want it to be the set that just contains 0 and 1. So only 2 elements in this codomain. And I'm going to try to define, and that's why I'm putting in quotes, this by saying f of x equals 0 if the input is in B, and f of x equals 1 if the input is in C. And suppose that B contains 3, 4, and 6, and C contains 4 and 7. Well, that means A, which is B union C, consists of all of those elements put together. So 3, 4, 6, and 7. Well, then suppose I ask the question, what is f of 4? So what happens if I plug 4 into this function? Well, the problem is that 4 is in both the B and the C. So it seems like the out should be 0 as well as 1. So what's f of 4? Well, it seems like it should be both 0 and 1, but we cannot have two outputs. But a function cannot have two outputs when you plug in one value. But a function can't have two outputs for one input. So this means this is not well defined. It is not well defined because there's a problematic input. Okay. So, at first glance, we might wonder, well, does stuff like this show up? Like, why are we even considering a situation like this? And the answer is, as we get more and more abstract in math, and we may have reasons to define things that we think are functions in much more abstract ways. And when we do that, it's not always going to be as immediately obvious whether something is well defined or not. And being able to test for it is important in those situations. Okay, so in the next video, we will talk about recursively defining sets and structures.